Hello and welcome to our physical sciences session. My name is Temba. Today we are focusing our attention on a very exciting part of chemistry which has to do with acids and bases. But what exactly are we looking at today in as far as acids and bases are concerned? We shall look at the theories around acids and bases as some of the common substances that we interact with on a daily day-to-day basis. Right. Now, we are going to look at acids and bases in terms of theories under the broader concept of chemical change, which is a very, exciting part of chemistry, but it has a lot of theory that is involved. So we'll look at the acid-base theories, okay? We shall also talk about the pH scale, if you say a substance is a base, exactly what is that based on in terms of, the pH scale? So as a measure of how strong an acid or a base is, we shall also, that will also be based on actual properties of these two classes of substances. However, the two theories that are very important that we shall focus our attention on are the Arrhenius theory as well as the Bronsted-Lowry theory. Right. Okay, without any waste of time, let's talk about the thought that's going to guide our session for today. Now, the question says, why are some chemicals classified as acids and others are called bases? Right, so that big question to say, what makes us say a particular, group of substances can be, referred to as acids while others are referred to as, bases? Actually, that has a lot to do with the properties, because based on the properties, we want to also try and explore that and see how best we can classify those two. So by the end of this segment, we need to be able to say why certain substances are actually acids while others are bases. Right. Okay, so that's the thought for today. So the terminology that we shall be using quite a lot in today's discussion, acid, is a key term in terms of classification. We shall also talk about base or bases, in terms of plural, as well as the pH scale. Now, if we talk of the pH scale, it's something that's not entirely new to us. We have interacted with the pH scale, earlier to say, okay, the values start from 0 to 14, and then there's everything in between. And then we shall also try and identify some of the common household substances, so that what the chemistry that we learn, we also try to relate it to, what happens every day around us. Right. Okay, so if we talk about the pH scale, we're saying it ranges from 0 to 14, okay? And then these values are actually an indication of acidity or alkalinity of a substance. So if we talk of the scale, we're looking at something that looks like this. So you'd realize that at pH 7, the pH value 7, we are saying that's the neutral value of pH. So if a substance like pure water, as an example, is a pH of 7, we're saying that we describe it as a neutral substance with respect to the pH scale. And then as you move further to your left, the strength of acidity increases. So substances that are closer to 7 are actually weak acids, while those are closer to 0, say for argument's sake, a hydrochloric acid of concentration 1 mole per cubic decimeter. That's a measure of the acidity of this substance. While at the opposite end, as you move from 7 to 14, the substances become more of strong bases. So you think of some of the household cleaners, different brands that we are familiar with, they have got a pH of between 11 and 12. Okay, so substances such as sodium hydroxide, with a concentration of 1 mole per cubic decimeter, actually is a strong base. Right. So pH 7 is neutral, pH closer to 0, strong acid, closer to 14 is a strong base. Right. So in terms of the measure, we can also talk about some of the the everyday substances that we can talk of in terms of pH. So remember, we are saying the pH is a measure. So pH is something that can be quantified. You can take a sample of a substance and actually be able to determine its pH value. Now, let's take, for example, from this simulation, we've got water, whatever volume of water. This is like 700 milliliters, which is 0.7 cubic decimeter. Okay, so if you add more water, you realize that the pH value is 7. So the volume of water has no bearing on the pH value. Okay, so it's actually per substance. And then we can take, for example, something like, let's say, for argument's sake, battery acid, right? We can add some battery acid and water, into that, okay? So that's the battery acid. As you can see, the pH value is 1.9. So this suggests that there's greater strength of acidity. So this is high acidity because this value is closer to 0, okay? And then we can talk of different substances altogether, which is still fine, right? Okay, just to go back to our simulation, right? We are also saying that in nature, many reactions, they occur in aqueous solutions. So we want to understand what an aqueous solution is, okay? And the most common solvent in which these reactions actually take place is water, okay? So the reactions of acids and bases, they take place in aqueous solutions. It means substances must be dissolved in water, right? And also, we're saying that substances, acids are substances that produce hydronium ions. So the formula for hydronium ion is H3O+. This suggests that if you come to think of it, hydrochloric acid is an acid, as the name suggests. So the hydrogen atom in the acid is actually bonds with the water molecule to give us the hydronium ion, okay? So this acid, which is hydrochloric acid, is a substance that actually produces a hydronium ion. So this reaction kind of details how these hydronium ions are actually formed. So, okay, so when a substance produces hydronium ions in solution, the process is ionization. So ionization is actually the process by which, acids, are break down in water to produce hydrogen ions. So by definition, ionization is a process by which a covalent, which is a molecular substance, they produce ions in solution for the first time. So this is what the definition says according to the Arrhenius acid-base model. So Arrhenius describes, the theory of Arrhenius describes an acid as a substance that produces hydronium ions in solution, okay? Right, what about bases according to this theory of Arrhenius, right? So these are substances that produce hydroxide ion. Take note, the formula of the hydroxide ion is OH minus. Now, take for argument's sake, if this substance actually, dissociates, what happens is, it breaks down, it will form this ion, which is the hydroxide ion. So this substance, sodium hydroxide, is actually what we would refer to as an Arrhenius base, right? Okay. And then it goes further to say that these substances which produce hydronium ions are referred to as bases. So the process of producing bases in solution is dissociation. So this is the reaction that shows how dissociation of a base occurs, so that at the end of the day, we can get our hydroxide ion, okay? Now, take note of the definitions, very, very important. So some substances, they don't produce hydronium ions in solution, but they are also basic, okay? So we can talk about different substances. Hence, there's a need to understand the theory beyond an acid and a base as a substance that produces hydroxyl as well as, hydroxide as well as, the hydronium ion. Okay, this takes us to the Bronsted-Lowry theory of the bases. So Bronsted theory says that an acid is a substance that is actually a proton donor. So this hydrogen ion would refer to it as a proton. Okay, right. So according to Bronsted-Lowry theory, any acid, because all acid contains at least a hydrogen atom. So in that sense, they are able to donate this proton, which is the hydrogen ion, right? Okay. Then bases actually proton acceptors. So there's a donor-recipient kind of a relationship between an acid and a base according to Bronsted-Lowry theory. Okay, so this actually happens simultaneously. So according to Bronsted-Lowry, the acid-base reaction are referred to as protolysis. So what is protolysis? Protolysis is a reaction that involves the transfer or exchange of protons. So that's as far as the acid-base theory. We need to explore more examples. Shortly after the break, we'll do certainly that and try to understand the application of this theory. Let's take a short break for now.